We're going to get started. First, I want to welcome everybody here tonight for our inaugural Don Ahman Memorial Lecture in Lighting Energy Efficiency. My name is Michael Siminovich, and I'm a professor here at UC Davis, and I'm the director of the California Lighting Technology Center. And I want to say first, it's a real honor to be here this evening in this memorial lecture to Don Ahman. This evening is to honor Don, our friend, and our colleague at the Lighting Technology Center, who was at UC Davis, who passed away tragically in March 2007. After his untimely death, there was a group of us who wanted to honor and commemorate Don in a special way through some type of program, scholarship, seminar, or lecture series. And this was really the genesis behind this evening. In the interim, there have been numerous meetings and discussions and efforts to put together a program that would truly honor Don's commitment towards energy efficiency and sustainability. And what has been created is the Don Ahman Memorial Lectureship, and we now have outstanding level of support and funding to offer this lectureship twice a year for many years into the future. I want to make a special thanks to all the folks that worked very hard on this and supported this lectureship. And this evening is our first lecture. Before I introduce our honored guest, Dr. Lorne Whitehead, I'd like to introduce Margaret Ahman, Don's wife, and I'd like her to say a few words before we get started. And I must say, Margaret has been very patient in the evolution of this program. So Margaret, please, would you come up and say a few words for us?
Thank you, Michael. Before I say a few words about Don, I wanted to thank all the people who had a hand in this. Michael and your staff for your commitment to remember Don with this event. Kelly for attending to all the details. All of you who contributed to make this possible and future lectures. And for each of you for coming tonight. While Don and I supported each other's professions in our careers and admired each other's achievements, I did not know him as a professional engineer as well as some of you in this room probably did. But I did know him to be a man deeply committed to energy conservation, yet overflowing with his personal energy. And those of you who knew Don are probably starting to chuckle. Don worked with energy. It was important to him to believe in the work he did, whether it was milking cows and much more on the farm in Wisconsin he grew up in, or helping in his father's construction business, or being a co-op engineering student at the University of Wisconsin at Madison, starting his career by moving to California to work in energy conservation at PG&E, or developing his skills over his career and his networks to excel as a consultant in HVAC and lighting and other energy conservation work. Don also played with energy, whether it was on bikes or skis, at home or in the mountains, and he enjoyed it most when he could share it with others. I'd like to relate just a few stories tonight. Don loved to tell stories, and so that even if you didn't know him, you will have a sense of the energetic man that he was. Our first backpack trip together was gorgeous but ambitious. It was in Yosemite. We were tackling 39 miles in 3 days. And I was experienced and willing, but on our rest day, the one in the middle, Don bagged a peak while I just sat by the lake. And by the end of the trip, I was going pretty slowly, and he, about a half mile from the car, ran to the car, dropped his pack, ran back down the hill, got my pack, and I was a little embarrassed but relieved that he carried it back for me. So that gives you a glimpse of his energy. He was kind of a self-proclaimed cheapskate, but he wasn't necessarily a minimalist. On another backpack trip with a bunch of friends, some of them definitely beginners, about 6 miles in and a mile from our destination lake, Don ran uphill with a pack again to find the best campsite, of course. He returned to our wearily plodding beginners and offered to carry any gear, and they just kind of shook their heads like, "You're crazy." As we cooked dinner in camp that night, everybody trying to recover from the day's hike, much to our amazement, Don pulls out a 1.5-liter bottle of wine from his pack. Do you know how much those things weigh? Who could top that, we thought. And we had a lovely dinner. The next night, you guessed it, he pulled a second 1.5-liter bottle of wine out of his pack. And you can imagine the expressions on our faces. Don loved to climb mountains and climbed several peaks in the Sierra Nevada and the Cascade, Whitney, Rainier, Ritter. He went up Mount Shasta 6 or 8 times, I'm not sure how many. He didn't summit every time, though, because his priority was safety and the relationships he had with his trip mates. But he always had that summit as his goal. He camped overnight on top of Mount Shasta once, on top of Half Dome twice, when it was allowed, and skied down Mount Shasta another time. He also skied across the Sierra, snowstorms and all. Don was also an avid cyclist. He rode the Davis Double Century, which is a 200 miles in a day ride from here, in 1985, and again in 2005, 20 years later. In between, he rode his bike across the United States by himself. While he never regretted that trek, he probably enjoyed more the many miles that he spent with friends and with his family, pulling one or both of our kids in a trailer or on a trailer-bike and eventually on a tandem. Don was passionate about family, friendship, enjoying the earth, and conserving its resources. In fact, he was pretty passionate about everything he did to help make this world a better place. So I want each of you to think of how we can channel Don's energy every time we ride a bike, walk, or take public transit. Reuse a twist tie or a rubber band. Don't want to waste anything. Teach a child a useful skill. Learn and share a time-saving keyboard command. That was one of his favorite things. Replace a light bulb with a more efficient lamp, of course. Or try to achieve balance between your personal and your professional life. Spend time outdoors with those you love, or otherwise exert a positive influence on people's lives and our fragile earth. Along with our children, Peter and Emily, who are here tonight, I thank you for being here to honor Don, to remember his commitment, his passion, and his abundant energy, and to learn more about how we can promote energy conservation. I invite you to continue Don's legacy. Thanks for having us here.
Thank you, Margaret. It's really good to have you here this evening. I would now like to introduce our speaker, Dr. Lorne Whitehead. It's very important to us that the inaugural lecturer for this program be a person that truly represented and shared the spirit of commitment and achievement towards energy efficiency. And I think this evening that we have brought the very person here that we believe would launch this program, and Dr. Lorne Whitehead is that person. Dr. Whitehead, professor of applied physics at University of British Columbia, is a true discoverer, academic, and professional that is leading the efforts on advanced optical systems for the purpose of lighting our buildings. Professor Whitehead has made a lifetime of outstanding contributions to the understanding of advanced optics and their configuration for the transport of light and the introduction of daylighting into buildings. Professor Whitehead has achieved an international reputation for being the key thinker in the evolution of advanced building systems and optics. I've known Professor Whitehead as a graduate student, young researcher, now older researcher, colleague, and now partner, and I have found him to be one of the most dedicated and hardworking contributors in the lighting field, and it's truly an honor to have him here. And I believe he best represents the spirit and the meaning we intended for the Don Ahman Memorial Lectureship. Please join me in welcoming Professor Lorne Whitehead. Thank you.
Well, Michael, thank you so much. It's a real pleasure to be here, and it's an honor to be here with you and to have the opportunity to help honor the memory of Don Ahman, your respected colleague. I have to just change the PowerPoint here, and with luck, we'll be able to get underway with that process. So my topic tonight is related to this idea of this idea of core sunlighting. And my proposal is to begin with a brief outline of the topics that I'll cover and then to expand. And the outline is really just to answer 5 questions, the 5 obvious questions about any idea. So core sunlighting, what is it? Why do I feel it should happen? How can it happen? And then the last 2 questions, when should it happen? And who should make it happen? And I'm not going to keep you in suspense. I'm going to begin by briefly answering all 5 questions and then expanding. So the first question, what is it? Think of core sunlighting as gentle indoor sunlight. So think of whatever it is you like about sunlight being brought inside and whatever you don't like being left outside. That's the idea. And I'll expand on that. Okay? The answer to the question, why should it happen, is a double-barreled question. A question that I think Don Ahman would have found very interesting. The first answer is to make a healthier planet, and the second answer is to help people in buildings be healthier. So this is the motivation, and it's the reason that I'm here. But of course, what we're working on in my laboratory and here at the California Lighting Technology Center is the question primarily, how is it possible to make it happen? And that question has a double-barreled answer as well. We need to find both efficiency and affordability. And by the way, there aren't a lot of academic institutions that tie those together, but success doesn't happen without tying those together. So I'll be talking about both those ideas. Now, here's a question. Can you guess what my answer is to question number 4? When should, now, thank you very much. Okay, here's a trickier one. What's my answer to question number 5? Who should make it happen? Us. Oh, I like that. I was going to say you, but that's but that's even more fair. Okay, so this is the outline. With your permission, we'll run through these. So I'm going to start with the what is it, and be just a little bit clearer. So in our focus today, this could broaden, but today we're really focusing on the workplace, lighting in the workplace, where we have the highest lighting levels. We need them for safety, for effectiveness. And so we have lighting codes that require reasonably high light levels in the workplace. And therefore, that's the place where we have the biggest energy problem. Also, we work by day when the sun shines. And so it's the place where there's the biggest opportunity to avoid waste. And so that's what we're targeting at. And what we'd like to do is to bring in to the commercial workplace, the place of work, light that has 4 simple characteristics. Those are affordable, it should be affordable, bright, healthy, and green. And of course, I don't mean the color of the light should be green, but that it should be good for the environment. Now, this idea of having something new, better in every important way, is something I feel very strongly about. For any new technology that is going to save energy, it really has to be good for people in every way. It has to resonate with people if we'd like it to spread rapidly. And so we think we have one of those opportunities here today as a result of new materials that exist. We have a way of doing something that has all 4 of these characteristics. So who wouldn't want to have light that is more affordable, is nice and bright and cheery, is good for you, and also is good for the environment? It naturally makes sense. So I'm going to cover those points actually in reverse order as I attempt to answer the other questions that I had in the list. So this question of why should it happen, it's good for the world, I actually doubt there's anybody in this room that doesn't already believe that. So I'm not going to take too much time on it, but the simple fact is electrical lights use electricity, and producing electricity is a problem from a greenhouse gas emission point of view. A lot of carbon pumped into the atmosphere, and it also costs money. Now, I could use words like kilo, mega, giga, and impress you with big numbers. I don't think I need to. I think most of you know that the people that understand the energy use of the country, in particular electrical utilities, recognize workplace illumination as a really big issue. It's a major source of pollution, and it's a major use of money. And the thing is, it shouldn't have to be that way. I mean, it's one thing if you've got a problem that can't be solved, but I mean, sunlight is clean and free. Okay, so surely there's a way that clean, free energy that's right out there, right outside the building, ought to be possible to be brought in when it's available and make life good. So from an environmental point of view, I think it's a no-brainer. In this talk, I'd like to emphasize a more controversial topic, and that is the question of healthy people. Now, this is a big issue. There's a variety of opinions on this issue, and I'm going to touch on some ideas that are not matters of fact, that are matters of conjecture. But nevertheless, I think it's worth talking about them, and why can't we talk about these things? So I'd like to begin that by making a statement that is a matter of fact. Electric lights in the workplace produce poor color. People can argue about how poor, but scientifically we know the color quality of electric lighting is poor compared to sunlight, which produces good color. And there isn't a lot of debate about that. There might be debate about magnitude, but not a lot of debate about that issue. So that part, I think, is fairly well accepted. But what's not accepted is whether it matters. And this is actually next week I'm giving a talk at the DOE's solid state lighting workshop where they've actually had a session called Color, What's All the Fuss? They've asked me to be a panelist there and talk about this. And so here's a preview of what I'm going to say. I'm going to say, in my observation at least in this issue, there are two very strong views about color and light sources. One view is that color matters a lot. There are people who feel this way very strongly. And by the way, don't worry, there's not going to be a show of hands, so relax. But there's another view that color matters very little, okay? And these views are really, sound like they are really in opposition. And the humorous thing, maybe humorous is the wrong word, the fact is both statements are correct some of the time. There are some situations where color is really not that important to people, sorry, I got my order wrong here, where color does matter a lot, but the reverse, others where it doesn't matter that much. Both cases occur, and it's confusing. You know, what does matter and what doesn't matter? And you might think to yourself, gee, you know, in elementary school, my teacher taught me orange plus red paint makes, red paint plus yellow paint makes orange, and blue plus yellow makes green, and I could make beautiful pictures, and I've never had much trouble buying paint and painting walls. And what's the fuss is a pretty reasonable question. So it is a reasonable issue, and the answer is there's a source of confusion here that is not apparent to people who aren't experts in the field. So I have a lot of contact with people who are experts in the field, and I wanted to give you just a glimpse, not to explain color, but to give you a glimpse of the issue. So don't worry, you're not going to have to understand this chart, but this is a chart that shows the process effectively going on in your visual perception system. When you look at, say, a green stoplight or a red stoplight or a green traffic signal, and you reach a conclusion about the color of the light. So there's a mathematical process effectively going on in an analog form in your visual perception system, symbolized by this flowchart. And even though it's integration and calculus and all this kind of stuff, it's a fairly simple flowchart, not that complicated. So the color of lights is not a complicated idea. Where things begin to get complicated is when you ask, what is the apparent color of a surface? So here's a surface of a certain color. It has a certain spectral distribution. What goes on in our visual perception system to perceive the color of a surface is way more subtle. What the eye is doing effectively is comparing the color of light reflected off the surface with the color of light effectively reflected off white surfaces and doing a ratiometric comparison that gives an answer that is remarkably stable. So people are able to sense and perceive and distinguish the colors of surfaces extremely well. Now, this is more complex, obviously, but this isn't actually the story. The story of light and color is the question of whether, it relates to the question of whether, if you change the light source, whether the perception of color changes. And that requires yet another comparison. So you need to compare what's going on with the perception of colors under light source A with what's going on with the perception of colors under light source B. Two sets of answers. You need a metric for comparing the differences and reaching a conclusion about how serious those differences are. That's the subject of color rendering, which is the subject of understanding the relationship between the light source and what we mere people see. Well, I can tell you, I believe I understand this, and I'm not bragging when I say that, it's just I've worked at it. But I haven't met a lot of people who are actually in the lighting industry that understand this, let alone those that aren't. So it's not surprising there could be disagreement. It's a hard subject. But what I'd like to do here is make it far more simple. So I'm going to simplify, and by the way, there's no insult intended in that. I'd just like to have something we can talk about in a few minutes. I'd like to simplify it by looking at one specific example. So the example I've chosen is the color of an individual's forearm. So one particular person in my laboratory volunteered to have her forearm measured. And the color of her forearm is represented here, I guess you could say symbolically, by a spectrophotometer measuring what's called the reflectance of the surface as a function of the wavelength. And you get the red curve that you see here. Now, the other thing we did is we took a picture of that skin and we printed the picture well. That is, we balanced the color in the printing process so that under a good quality illuminant, which I'll mention in a moment, the color matched perfectly. So picture this. Picture you've got a photograph, say, of your finger, and beside it you put your finger and you look at them, they look the same. And you go, well done, well printed, good color. Okay? That's step one. Step two is we had two light sources to compare. And what I'm showing here is a light source, the blue curve, which is considered to be kind of the gold standard of color quality. It looks actually very much like the spectral distribution as a function of wavelength of sunlight kind of late in the afternoon. You know, that sort of golden time when the sun gets a little bit warm. That happens to be that color. It's probably the most popular color for really high color quality lighting. And what's shown in the purple curve is a different light source. This is 3 light-emitting diodes, blue, green, and red, that have fairly narrow spectra. Nothing intrinsically wrong with that. It's just different. But they are adjusted in their intensity to produce the same color. So picture that. Even though these look different, doesn't matter. You can't see spectra. Okay? If you see the light coming out, they look identical. They cannot be distinguished from one another. Okay? So then here's the question to you. If you have identical looking spectra, they're different spectra because they're different materials. The dyes in a photograph are different than the pigments in skin. They're different looking spectra, but the samples match perfectly and the light sources match perfectly. Then here's the question. If the two match perfectly under this very high color quality light, will they match under the different source, under the light emitting diode? The answer is no. At least the answer is not necessarily. They might or they might not, and that's the issue of high quality color. So in fact what happens in this particular case, and you can do it, but you can also calculate it very accurately, is the color in this color dimensional space that isn't really important matches perfectly for what's called the Planckian radiator, this radiator. But when we switch to the LED, they shift, the color shifts, but maybe more seriously, it shifts differently. So the color of the skin goes to here, and the color of the photograph of the skin goes to here. So if you walk from an office where you've printed a photograph with good color balance and it matches things, and you walk to another office lit with a different light, it doesn't match. Okay? And at least it may not match, and that's the issue of color quality. And just to put that in perspective graphically, I'll try this. What I have here is a depiction of the color, but it's not calibrated for this projector. So don't worry about the color too much itself, but more just the relationship of the colors. On the left is a depiction of the photo and the skin. I can't actually remember what the actual skin color was. It probably looked a little different than this, but it doesn't matter. But the point is, this is under the Planckian radiator matching perfectly. And the differences here are calculated correctly, showing how there's a shift in the color going to the 3 narrowband lights for the photo color, and a different shift for the skin, so they no longer match. So this is just graphically pictorially showing what's up in the graph here. Okay, so if you have poor color quality light sources, colors are wonky. Okay? Now, I mentioned there were 2 sort of dominant views on this topic of wonkiness of light. And I guess the way that the views might sort of be expressed right now would be to say, on the who cares side, sort of say, well, look, if for any reason it happened to be true that this light was cheaper or more efficient or lasted longer or whatever, right? If it saves anything at all, then who cares if it makes a skin look a bit funny and makes fruit look a little bit funny? You know, suck it up. That's kind of one view, okay? Pardon the rude comment, but that's a view, a kind of an expression that you can hear. The opposite view goes kind of like this. Our most important human sense is vision, by far. Color is one of the most aesthetically important components of vision. And many people get a great deal of joy in life from the subtleties of color. And the idea, when we're dealing with very small amounts of money, really, the idea of forcing people to be exposed to distorted color in an effort to make a better world is perhaps misguided, if there's a better way. And of course, we're here to talk about a better way. But those are the two different views, okay? And I have very good friends and relatives with both views, and of course all the ranges in between. I think I understand and respect them. But they are kind of different. And into that mix, tonight I'd like to throw one more thought. And the thought relates basically to the topic of what matters and what doesn't for people. And sometimes it's not obvious. Sometimes we might not guess. And I'm going to show you a visual demonstration of this. You're going to have to be very sharp with your eyes here. Look at the screen. On the screen, I've got a picture. It's a schematic representation. Imagine that you're looking at some buildings on a hill. Okay? So those are just buildings rising up, drawn deliberately, very, very simply. And I'm going to change this image. I'm going to make the picture disappear, and when it comes back, something's going to be different. See if you can see what it is. So disappear, and now something's different. Did you see the change? I see just a few people who saw the change. Let me try to make it clearer. I'm going to go back now. Buildings are going to go away, and now we're going back to the way they were. The change has now disappeared. Okay, not a lot of people could see it. I'll tell you what the change was. In the middle slide there, everything was made bigger by exactly 2%. Now, if I'd made it 20% bigger, you would have noticed it. 2% bigger, most people can't see it. Now I'm going to do it again, and we're not going to do this all night, but I'm going to do it one more time. And when it comes back, something else will be different. So it goes away, and it comes back. Anybody see a change? What's the change? Skewed. Something is skewed. For anybody who doesn't see it, I'll make it more obvious right now. Without even making it disappear, I'll switch back to non-skewed. What would you guess is the skew angle? 2%. That's a good guess. It's actually 1%. So when it comes to skew angle, comparing verticals, people are far more sensitive than when it comes to magnitude. And there's a very similar thing that goes on in the world of lighting. People are actually relatively insensitive to amount of light. We can tell if it gets brighter, but we're relatively insensitive. But and also we're relatively insensitive to the color of the ambient light. It doesn't really bother us that our lights indoors in the evening are kind of yellow compared to outdoor sunshine. Nobody minds. Nobody cares. In fact, maybe it's a good thing. But when it comes to the color rendering of surfaces, people care a lot. I think it's probably because those that couldn't tell the difference between poisonous berries and safe berries died. And so we have evolved the ability to judge surface colors very, very accurately. Now, what does this have to do with daylighting? Well, the connection is related to an idea that I call perceptual dissonance. And the idea basically goes like this. It says that when people perceive things that don't match their innate expectation of what they should perceive, they can feel sick. And the classic example, the best known example, is motion sickness. What happens, sorry to even bring it up for those that suffer, what happens with motion sickness is your inner ear experience of angular acceleration doesn't match your visual observation of angular acceleration, and it makes many people sick. The theory for it is that, again, this is evolutionary. The evolutionary theory is that one of the first symptoms of digesting a neurotoxin, which is a very common problem with plants that are not good for you, is perceptual mismatch. It affects affects your nervous system, can affect the way you perceive things, and so getting that out of your system would be a good idea. So this may or may not relate to lighting, but here's what we do know. There are a lot of people that when they report they don't like certain lighting, they say that it makes them feel unwell, it disturbs them. Not everybody, but it seems to be a common feeling among many people, and those that feel it relatively strongly. Now, and another related factor, which is also even less debatable, is that skin color shifts can make people look unwell. It's kind of a gruesome topic, but scientists have studied the skin color change associated with disease, such as jaundice, for example, or anemia. They've also studied the skin color change when we die. And they call that pallor mortis. How's that for a gruesome term? And it turns out that the magnitude of pallor mortis is bigger, but not a whole lot bigger than the color shifts of skin associated with electric lighting. So you could say the wrong indoor lighting can make us look half dead, or at least make us look unwell. So, the combination of people potentially thinking they don't look good or they don't feel good, it sounds funny, but it's deadly serious. There's a whole field of medicine called psychosomatic medicine that says these kinds of ideas can be bad for us, and even if they aren't bad for us, they aren't any fun. And feeling good indoors is important. One last factor that relates to this idea of perceptual matching is to think back to our evolutionary past in and near the savanna, where it wouldn't be at all unusual for a person to be in the safety of a forest area looking out at the view of the open savanna. Much like in our workplace today, we're in a building looking out at the outdoors. Well, in that natural setting, when the sun goes behind a cloud or changes brightness in the course of the day, the light level in the forest would go up and down in correspondence with the light level outside. They'd kind of match. And so this is kind of a normal thing, and there's, I think, a reasonable belief that that correlation of overhead lighting with outdoor lighting makes sense. So on the basis of all of this, admittedly plausible conjecture, it's just plausible arguments, they are not proven, but they all add plausibility or perhaps understandability to what people say. What do they say? Many people say they prefer daylight. So, it might not just be, an opinion. It might be more than that. And those that say they prefer it, many of them feel deeply that it is the right thing. So my feeling is that we're on the verge of more data. It's premature to say that daylight is healthier, I think. But it's plausible that the people who feel it's good for you are right. And even if they just feel it's good for them, that's important too. So shouldn't we respect them? So I guess my comment here, honestly, would be to say to those that for years have had a hunch that color matters and that good lighting matters, you were probably right. And to those that took the attitude of, who cares, I guess I'd kind of say, maybe it's your turn to suck it up a little bit and think, we should try to respect. And the thing is, the lucky thing, this is the good news. There is no battle here. We have a solution that can do it all. So we can have light that is efficient, is cost-effective, is daylight, and has all of these benefits. And so that's, of course, the purpose of the rest of the talk. But I wanted to take a break and see how you feel about this sketch. It kind of summarizes where we're heading here. So I hear a few chuckles. Some people find this a little amusing. I talked to the artist, Mike Baldwin, and I told him I had a reason I would like to show this at presentations, and he gave me the right to do so. So this is a legally presented work of art. My question to you is, I know why Mike Baldwin thought this was funny, is who would pay $20 to get a tan at a beach when you can lie in the sand for free, right? So that's the obvious humor here. Anybody have a suggestion of the other thing that I find funny about this? Any thoughts? Sorry? Absolutely. There's nothing natural about this. You could have natural light at the beach and you're having something unnatural. And worse yet, this is the really sad part, you're taking sunlight and converting it to electricity inefficiently and expensively with photovoltaic cells. And now you're taking that precious electricity that, if anything, should be running a computer or a fan or something like that, and you're inefficiently converting it back into light. So it's an extremely inefficient, not cost-effective process, giving people something they don't want, right? And that would be funny if it was just happening on the beach in a cartoon. But think about it. It's happening in every city around the world every time the sun shines. And I'm completely convinced people will look back at us today and say, unbelievable that they would do that. You know, it's just amazing that they would do that. So that's the topic. And I'd like to now talk about how it can happen and go to that first point about efficiency. Now, it has to be efficient because there's only so much sunlight that hits a building. And it turns out, isn't this an interesting coincidence, there's just enough light hitting the surface of a building that if you can fairly efficiently grab it and bring it inside, you can turn off the lights. Nature didn't give us 10 times more light than we need, so we have to do it well. But we got just enough. The sun's just bright enough that we can actually do this thing. And the way it's done is pretty simple. We have to capture light on the outside of a building. So there's a sunlight tracking and concentration system that captures the light. And then we need to pipe the light inside. So there's a piping system that takes that captured light and brings it inside the building. And I'll show you actually a video that'll show this more clearly in just a moment. But that's the basic idea. And I'd like to start by talking about the efficiency challenge of the piping. Not a lot of people would think intrinsically that you can pipe light, but it turns out you can. And I've been experimenting with piping light most of my career. It's kind of an interesting topic if you don't have something better to do. But basically, the way you pipe light is you take a hollow tube, you line the inside with mirrors, and you just need to make sure the mirrors are really shiny. So you need an extremely efficient reflector. Ordinary mirrors are not sufficiently efficient. And so one of the first developments that made this practical was to find a way of not using a reflector which even at 95% with 10 bounces loses almost half the light. Can't do that. So it turns out there's a trick with optics, a well-known effect with optics, where light rays, when they hit a surface, a transparent surface between two materials, like, for example, plastic and air, can reflect, if the angle is steep enough, they can reflect by an effect called total internal reflection. And it's 100% efficient. So the first trick in solar lighting is to take advantage of total internal reflection in structures that can be made big and hollow. So there's a need to, for what we're doing, we have to carry lots of light, so we need big hollow structures where we can combine TIR and hollowtude to make something work. And the way we do that is basically with prismatic surfaces. So there's a manufacturing technique for making microscopic prismatic surfaces that can, with the right geometrical characteristics, can be made into a tube that can be round or square or rectangular, actually almost any shape you want. And as long as the light is within a certain range of angles, it's carried really efficiently. Interestingly, if the light is outside that range of angles, it escapes really efficiently. And that ability to pipe light, but then also get it out, is the critical characteristic for light distribution in buildings. And we do the getting out in a kind of an interesting trick. Well, the light guide looks like a ventilation duct, a shiny, plasticky, prismatic-y looking ventilation duct, usually hidden inside a cover. But if you look at the actual thing itself, it's this glassy thing carrying light. And the way we get light to jump out of it is inside it we put what we call extractor panels that are diffuse reflectors that have the characteristic that when light hits them, the reflected light is scattered at angles that lets it just escape, comes right out. So we have a tremendous amount of control over that escape rate by simply varying the size of the panel. And this lets us arrange it so that all the light that enters one end of the pipe escapes as it travels along, and it does so uniformly. This engineering challenge is very much like ventilation engineering, where you're trying to get the same amount of light coming out of a ventilation duct all the way along, but the pressure is dropping with distance. So this is a technique that's analogous to that, and it works really well. So you can get really efficient and uniform distribution of light coming out of a very wide range of lengths of light guides. There's another trick that's important, though, and that is, this relates to efficiency. It's desirable to be efficient as a light structure, both for the light that we're carrying from the sun and also for electric lights that we would like to put inside these guides. And again, we'll show you this in a moment. That requires another new material in the field of lighting called multi-layer optical film, which has a reflectance value of over 98% for all angles of light. So what we've actually developed is a hybrid structure that uses multi-layer reflective film on the top and sides of a hollow guide and prismatic film at the bottom. And the neat thing is then inside the structure, we can put either fluorescent lamps or soon LEDs. Any light source we want actually can be used electrically in the same structure, so that we don't have to have one system for piping sunlight and one system for electric light. They can be the same system. So it's double duty. You already have to have electric lights. Why not use them for also carrying sunlight? So that's sort of the efficient and practical idea. And these things, when you build them, they can have a wide variety of sizes and shapes, but they look like light fixtures. They're made, we have them made by a light fixture company. The thing that's new is the films that go in, these new, very efficient materials, but they go in the same way a light fixture company could put in a conventional reflective film. So there's nothing too fancy about that. And it works really well. I've been talking about color, so I thought I should show this. This is a graph showing the spectral distribution of the sunlight in the guide at the beginning in solid and at the end in dotted. And they're indistinguishable. They're very accurately the same. So we really are bringing truly natural daylight into the building. And lots of sizes and shapes of these things, as I mentioned, but these are some recent experiments that have been done by a light fixture company that's kind of getting interested in this. Here's an example, and this actually is an example on the inside of the building of what you'll see in a video in just a couple of minutes, showing a place where there is no electric light. The electric lights are there, but they're not on, and the lighting is coming entirely from the sunlight. Of course, the energy-saving part needs to be verified. So we've done a lot of work with our local electrical utility, BC Hydro, and also had a lot of conversations with the folks here at the California Light and Technology Center on the verification front. And there's lots more work to do here. I'll come back to that toward the end of the presentation. But the long story short is it works fine. When the sun shines, the electric lights turn off. We've measured the extent to which that's true. So for example, we've taken weather data at the same time that we've recorded system performance. From the weather data, we've measured the time that the sun was available, and we've measured the time that the lights were off, and they've matched. That was true on a mostly sunny day. This is another day where the same measurement was done on a partly sunny day. And there's good agreement, and the conclusion from that good agreement is that, good, the lights turn off like they should, but yes, the savings match expectation from current weather data. It would be surprising if they don't, but it's important to check that they do. And the conclusion from that, admittedly a small leap, is that anywhere that we have weather data, we can probably make a pretty good prediction. And that has yet to be verified because, of course, we're at the early stages, a point that I'll also come back to at the end of the talk. But it's certainly looking very good from a measurement and verification point of view. So now I'd like to move on to this academically dreaded topic of affordability, because academics are famous for doing things that don't make sense economically. And I can tell you I would absolutely not be here today if I did not absolutely believe this makes sense. So before I became interested in this, that was job one, was with real manufacturing engineers to ask the question, can this be sensible? And it's a tough question. It's not an easy one. One of the reasons it's tough is you have to ask the question, how inexpensive does this have to be? Now, with everything I was saying about color rendering, I also want to say this. In my opinion, the way to argue that this should happen is that it makes sense economically. It doesn't have to be the right thing to do for color. And also, it's the right thing to do for color. It needs to be both, okay? So it's very important to ask the question, if color didn't matter, would it make sense economically? Well, what would the savings be? So here's an example of a system where one light guide lights up 660 square feet. The lighting load, say, is a watt per square foot, so you're saving 660 watts when the sun shines. Let's say you've got 2,080 hours a year of potential operating time for the system and 40% sunshine, much less than you have here in Davis, for example. And you get a savings of 549 kilowatt hours per year, which to those that aren't in this business might sound like a big savings, and it is a big savings. It's important, but electricity can be inexpensive. In some areas, it can be as low as 6 cents a kilowatt hour. And so that only turns out to be a savings of $33 a year. Now, I have deliberately downplayed that number as low as I possibly can in every way. But I've used a very low sunshine availability rate, and I've used a very low cost for the electricity. I've left out air conditioning costs, which are often associated with the waste heat with lamps. I've left out peak load charges and a lot, okay? So the real number, certainly here in California, the real number is much higher. But I wanted to kind of shock you with this low number. I hope you find it shocking. What this says is the system is only, if it's only saving $33 a year, sure, you can save up that savings for a certain number of years, but not 1,000 years, not 100 years, maybe 10 years. 10 years seems to be a good number these days in some parts of the green building community. So, you know, that says that you can afford, in this case, that would mean you could afford $330 for the differential cost of catching the sun. Now, the rest of the system has other uses, so you don't have to pay for the whole system, but for the extra cost of the sun, you've got $330. Is that possible? Yes, it is. So the nice thing is the system can actually be inexpensive, but it doesn't come easily. If you just look at the cost of commercial optics, it's way more than that. This can't be like buying a telescope. It has to be more like buying a window, okay? In fact, it can't even be like buying a window. It has to be like buying a slightly better window for reasons that make sense, which of course we do, okay? So the challenge is how to figure out how you can make something that doesn't cost too much. And this achieving of cost effectiveness, I believe, is an area for technical innovation, and I think it's a role universities actually should be playing more. The design of the system is very, very critical here, and there are two big issues, two simple issues that I think are worth understanding. One concern is that it costs you money to concentrate light. So we've got, you know, lots of big area of sunlight outside the building, but we want to squeeze it down. But squeezing it down requires optical precision, and optical precision costs money. So this is one problem, but the more we squeeze it, and it's nonlinear, the more we squeeze it, the more we have to pay for the squeezing. But on the other hand, if we don't squeeze it, then we've got a pipe, then we have to have a giant pipe. And a giant pipe carrying light into a building uses up space in the building, and that's worth a lot of money. So there's an issue either way, and what's the answer when you've got two opposing forces? Well, obviously compromise is a good thing to try. Sometimes compromises work, sometimes they don't. In this case, they do. And I'd like to show that to you pictorially. This is a schematic graph, but basically what it's saying is, here's an idea of what it costs to concentrate sunlight. This is the concentration ratio here. So if you want to concentrate sunlight 100 times, it's way more expensive than if you concentrate it less. And the cheapest thing is not to concentrate it at all. The flip side of that story I just told you is the cost of delivering sunlight, because the pipe gets bigger if the concentration goes down, is this curve, conceptually. So unconcentrated is bad from that perspective. The sum is the actual cost, and when you add them together, you get a curve that has a sweet spot. So it's that line of reasoning that led us to the design we have, which is a sweet spot of a concentration level of about 10 suns. When the sun is concentrated times 10, if you put your hand in it, what do you think it feels like? Fine, it feels warm. You know the feeling when you're at a campfire, that warmth, you go, oh, that's nice. You don't want to leave it there maybe forever, but it's a gentle, you know, it's hotter than sunshine, but it's not dangerous. Times 100, I don't know if you ever had friends as a kid that burnt bugs with magnifying glasses, but, you know, I don't know if you want to go there, but we don't want to go there economically. From a practical point of view, this is a nice place to be. So that's where we're operating. And the result has been systems that manufacturing engineers tell us can be cost effective. The way the tracking is done is with arrays of mirrors. The video will show this in just a moment. And the arrays of mirrors are led to concentrating lenses that concentrate the light into little pipes that join a bigger pipe that then leads into the building. So it's plumbing. And here's the neat thing. The plumbing materials are extremely lightweight. They're in an enclosure that keeps out the weather, keeps out the rain and the wind, and also the little moving parts that are there are some moving parts. They're designed with an expected operating life of hundreds of years. It's easy to do that, it turns out, because they move so slowly. So, you know, it's a funny thing. For people who are in the moving parts business, who of course are the consultants that we work with in analyzing all of this, it's all a piece of cake. Like once you figure out this is the way to do it, it's actually easy to show it can work really well. And so building it has gone flawlessly, and the things are working really well. This is just a demonstration of one place where they were demonstrated, and I thought this might be a time, I've been talking enough, I thought I'd take a break before we have sort of the wrap-up 5 or 10 minute conversation, just to show you some video that depicts this. Now, to do that, the video also has sound, and I'm going to see, there's a good chance you'll be able to hear it. If not, you'll see the pictures. Here we go.
Well, you don't have to look through garbage to find ways to be green. Just look out your window tomorrow and think about this. Wouldn't it be nice to use the sun to light up office buildings instead of fluorescent bulbs? Frederick Zalak spoke with a Canadian researcher whose new concept might just make this a reality.
It's around noon and thousands of people are working in Vancouver's downtown skyscrapers. It's a beautiful sunny day, but inside, artificial light rules, even near the windows. All of those lights add up and make up 1/3 of the energy consumption of these towers. A University of British Columbia research group wants to reduce this waste by using natural light. Physics professor Lorne Whitehead got the idea in this lab in 1978 when he was still a student.
It was a beautiful sunny day, and I was working in a lab that had no windows. And I thought to myself, this is crazy. It's crazy to have electric lights burning in offices and laboratories and places like this on sunny days when the energy we need is just outside the wall. Surely there's a practical way to bring it in.
It took several decades before Whitehead would find a solution, but in the meantime, he learned to play with artificial light by using various materials. He designed a system to pipe light, which is being used on the McGill Tower in Montreal and in this Boston tunnel. The same concept can be applied to illuminate downtown offices with natural light, but harnessing the sun raises new challenges.
In order to pipe the light, we need to have the light traveling horizontally into the pipe, which is a problem because the sunlight's coming down. And we also need to concentrate it into the pipe, because ordinary sunlight, while it's quite bright, isn't bright enough for our job. We need it 10 times brighter. Just blocking the light from hitting the white screen.
His solution? A solar canopy that we see here in a scaled-down version. This device collects sunlight with an array of small mirrors. The mirrors slowly rotate and follow the sun as it moves across the sky, just like a sunflower would. The sunlight is reflected by these mirrors. It then goes through pipes and lenses that act like a magnifying glass, concentrating and making the light 10 times brighter. It enters a long and narrow light guide similar to an air duct located in the ceiling. The inside of the duct is covered with this reflective film so that the sun rays can travel as far as possible in the building.
So it's a matter of efficiently carrying the light with special mirrors and bringing it out in a way that falls beautifully into the place you're working so that it feels like daylight coming from the sky.
Whitehead's team built a prototype. They had to try several designs to find a way to smoothly move these mirrors without wearing the parts down. Then the real test, fitting the system onto an existing building in Burnaby. It's installed on the south side where there's the most sunlight. A small computer is programmed to move and direct the mirrors at the sun at all times. Light enters the duct and travels up to 25 meters inside the building. At first glance, it looks like any other office space, but a difference is visible to the naked eye. The color of the light is different from artificial light. These office workers are experiencing it for the very first time.
I like it. Yeah, it's relaxing.
The surprise is how it felt. It feels wonderful. There's something about being in a room lit with natural daylight, that sense of contact with the outside world and the quality of the color that I can't describe, but it's very real.
And when clouds block the sun, fluorescent lights automatically turn on. They are installed in the same duct in the ceiling. The solar canopy is more efficient than traditional solar panels because it doesn't have to convert sunlight into electricity. According to the team's estimates, the solar canopy could reduce the amount of energy used for lighting by at least 25%. And that's just for Vancouver, where sunlight can be hard to get in the winter. Savings could be even higher elsewhere. But such a new concept can be difficult to sell at first.
Buildings in the construction industry, for obvious reasons, are conservative. Buildings have to last a long time. You want them to work. And so there's a need, kind of a desire to see it done somewhere else before you take a chance and do it. And that's where demonstration projects are the key.
By reducing the width of the canopy, the team hopes to fit it entirely inside a building. If the trials are successful, this new green technology could one day brighten our workdays by letting the sunshine in. Frédéric Zalac, CBC News, Vancouver.
So I hope that's helpful. I thought just actually seeing it physically could make it a little bit more concrete. And now I'd just like to wrap up with a few concluding thoughts. I mentioned the when it should happen and the answer now. We're getting underway. So we are in this demonstration phase, as the video was describing. There's a new spin-off company that's been created from the University of British Columbia, actually with a bunch of my students and a bunch of other outside experts and investors and stuff like that. And they're trying to get this going. And there are other companies also that are very interested in this. And it's actually good collaboration between those companies. It's a very early sort of pre-competitive situation. So there is commercial interest, so that's one very exciting thing. And in fact, SunCentral has achieved government funding to collaborate with partners in various places, including here, in doing some demonstration projects. So you just saw one of them in the video. A second one is just under completion. In fact, it was completed last week at the University of British Columbia in the Biological Sciences Complex in a laboratory building. So we're excited about that. There's a new building under construction that'll be opening this summer in a university campus in Penticton, British Columbia. And then we're very excited about a project that we were just meeting about. In fact, a project here at UC Davis in the USDA building. And Michael Falcon, the person in charge of that building, is here actually this evening. We're very pleased with that. And he is very excited about a demonstration project there. So that'll be the first significant U.S. demonstration of this technology, other than laboratory work, which has already been underway here at the California Lighting Technology Center. So these things are just getting started, and they need to continue. And this brings us, well, I think that answers all of the first 4 questions about what's going on here. But I left out that one about who should make it happen. And this is where I'd like to wrap up with this threatening comment, you. And I'd like to explain what I mean by that. And I mean it in the nicest way. There are several things. In fact, I think there's an argument that the people in this room here have far more power to advance this technology than probably any other group I've spoken to, for a variety of reasons. One reason is the jewel that you have here at the University of California, Davis, called the California Lighting Technology Center. And, you know, it's a funny thing. People so often don't appreciate what they have nearby. They tend to assume that what they have nearby is good, but, you know, kind of typical. And I can tell you, I travel, you know, the world and meet with experts in lighting all over the world. And what you have here is unique. It's a fabulous center doing fabulous work that needs to be done. And certainly it's very influential in this area. So already the folks here have made a big difference, and I know there's going to be more of that. So there's something you could do right away. Support the California Lighting Technology Center in whatever way you're able to, and you'll be advancing not just this, but other very important energy efficient technologies. But there's another aspect as well, where there may be some in this room that could help. And that is, and this is nothing about this particular technology, but for technology generally, crossing the chasm, as they describe it, you know, this challenge of getting from demonstrations to widespread acceptance is difficult. The reason is very simple. We know this technology in commercial scale mass production will be cost effective. So once it's in mass production, it will stay in mass production. There's no going back. The problem is getting there. because right now it's not in mass production, and so these demonstration projects do cost more. Now, a few demonstration projects, that's up to government, and government has stepped up, so they're happening. It's that next level, where you get the next, 5, 10, 15, 20 projects around the country, where the private sector has to step in too. Individuals who are, willing to use their own money to pay a little more, not a lot more, but to pay a little more to do something new and of the future, need to do it. And I kind of think there's an analogy, kind of like in the art world. If you think of the people who buy original artwork, not everyone does, but a lot of people who can afford to like to buy original art. Why do they do that when they could buy reproductions? And the answer is partly, for some people perhaps, is prestige. But for other people, it's being part of something important. We wouldn't have an art community if people didn't buy original art. It's a very important part of our society. And the same thing is true for the new adopters in important new environmental technology. We need people who would like to be part of the future and who'd like to be associated with that, but more importantly, would like to be part of it happening. And it's quite possible that in this room there are people that know people or people who are in a position to have influence in this way. So that's another way that you can make a difference. And then, of course, I don't have to mention election time. But, and not only that, but of course California, being in a tremendous leadership position worldwide on environmental matters, you as Californians have the ability to influence colleagues in other states and other countries to vote for people that care about this sort of thing and can make a difference. So there's lots of ways actually that I believe that it's true that you can make a difference. So I hope that I've answered the questions that I intended to answer today, and I'd love to answer some more. So I'm going to stop at that point for that purpose, and thank you, sincerely thank you for your attention. Thanks. And in terms of managing questions, I don't know who's in charge, so let's just see what happens. But any questions would be most welcome. Yes?
What would be the trade-off? How much less deep could you go if you didn't concentrate and track the sun?
Excellent question. This has been carefully investigated. In fact, there's a good group in Switzerland that's done a lot of work on that topic. They don't track the sun. They use a system they call the anadolic ceiling. And they get in, I think, typically about maybe 20 feet. But it's not with a very good distribution. So that's a rough number. Now, I should say there's another technique for getting further in, and that's simply to increase the floor-to-floor spacing. And this is very common now in certain styles of green construction, to sort of push that limit. If you're willing to increase that spacing enough, then you can get quite a bit of light penetration from the side. There are two difficulties with that. One is the cost. We've done very careful calculations on that, and the increased fenestration cost is high, both because of the increased amount of glass, but also because you have to use much more expensive windows to deal with the increase in glazing, the increased heat load and minimizing the heat load. So it's not an economic solution. Basically, to put a long story short, we haven't found another method for getting the light into the core that is more cost effective than what we're suggesting. It is true, there is a cost in the concentration, but if we keep it reasonable like we are at times 10, it's a surprisingly small cost. Yes?
Did you look at all at vertical penetration?
Yes. Oh, great question. Absolutely. In fact, when I first got into the field, I figured that's exactly what we would do all the time. And we can do it. So if anybody wants to do it, no problem. The only difficulty with vertical is, first of all, on tall buildings, there's a limited amount of space on the rooftop to collect the light. And some feel that that's maybe a better place to put photovoltaic cells, where you can run wires really easily through the building. But the other thing is, even if you have enough light up there, you have to penetrate vertically, and that takes architectural space to do so. And so that's expensive space. And in buildings, the least expensive sort of cubic footage that's available is up near the ceiling. And so that's why we're focusing on that. But absolutely, it can be done. Yes?
Beyond rectangles, are circles, were you saying earlier, circles?
Totally fine.
So there's
Any
quite a
cross
different
section.
shapes.
Very back there, Jonathan?
That's why they call them runners. My question is, you've done a lot of parts of this before. You've commercialized a number of different optical technologies with, I think, remarkable and exemplary success. To my knowledge, this is the first time you put together a whole system and commercialized it. And my knowledge is partial, so you can second guess me on that. But I'm just curious, since you've done commercialization probably more than most people in the academic world, or even most people, period, what are the stages that you see coming? Can you give us a little bit of a crystal ball look at what might lie ahead?
Absolutely, and I think every case is probably different. And so what we've done in this case is we've gone to the experts. In fact, we had a really nice brainstorm session with a leading green architect who is very knowledgeable about the construction industry, and particularly the future of the curtain wall industry, which is a key issue here. And his strong recommendation actually is that this spin-off company, which I don't control, but is now taking this away, should focus on relationships with the curtain wall manufacturers and say, look, you people are already in the business of making quite high technology things that get bolted to the building and make the wall. And all we're talking about is offering something that gets built in to the non-window spandrel portions of the curtain wall, where currently solar energy is wasted. And you build this in and then supply it. On the other side, you mentioned, Jonathan, the system. On the other side with the lighting, the hope is the lighting fixture world will just step up. It's so easy. We do have one company, it's probably not appropriate to mention the name, but a company which is owned by a big company that believes this should happen and is keen. And there will be others. There's no intention to go exclusive there, so there'll be, we hope, a wide number of lighting companies that want to do it. And this, what SunCentral and others will be enabling is just kind of like a different kind of plug. Instead of plugging in to get into the wall to get light, imagine plugging into the wall to get electricity, plugging in to get light, and connecting it to your pipe, and away you go. I don't know if that's answered your question, but hopefully. Yes?
Right, it's really easy to get sunlight 25 feet into a building, but to maybe 100 feet would be a lot more difficult and a lot more expensive. So how could you sell this type of technology to large buildings where sunlight might matter, like hospitals, for example?
Oh, very interesting idea.
And can you use fiber optic wire to get the light indoors more efficiently?
Okay, so two very good questions there. The answer on hospitals is it's quite likely a possibility. There certainly are places in hospitals that have no windows, no natural light, and if you care about health, there's a place that you might care quite a bit. So thank you. I think it's a great idea. And there are lots of places like that that are probably particularly suitable. To be honest, our main emphasis, and this is more not so much from a business perspective as my environmental interest, is the places that use the most electricity. So we've tended to think of the kind of standard office building as one of the areas where there is the biggest use. But anyway, it's a very good idea. Now, completely different question, but a good one. Why not use fiber optics? Because we all know optical fibers. Turns out optical fibers are just terrible for this job. Now, I don't want to be critical because they're very good for certain things. For example, if you want to carry a little bit of light a short distance, they're fantastic. We're very interested in using them possibly in the last leg. There might be some situations in our system where the fiber would be a really good way of taking a bit of light out of the main duct and distributing it. But when you take light 30 feet, 40 feet, 50 feet in optical fibers, there's a lot of loss. And not only is the optical loss unfortunate from an efficiency and a cost point of view, but it colors the light. So now you don't have natural light anymore. And the whole purpose, one of the most important purposes, was to have unfiltered daylight. I'm not sure if anybody would like to take charge of who answers in what order. Michael, would you like to? I don't want to offend anybody, but there's several hands at once here.
I wanted to say, before we finish tonight, we have food and drinks after the lecture and the questions. So I encourage you all to stay for more conversation and questions. So let's take a few more questions, then we can adjourn for drinks and food. So,
how will you convince people that the tracking mechanism will last for 30 years?
Excellent question. So I have one answer. I almost don't want to use it because there are people in this room that have heard me say this many times, but I hope you haven't. So here's a stock answer. What if I could show you in this room a moving part that is certainly going to outlast the normal life of this, by the way, fabulous building. It's a great, great place. And the answer is the hinge on the door over there. So hinges don't wear out. Now, a hinge is a moving part. Turns out that the hinge in a door has to take tremendously more force than the moving parts in this system. And it has to move far more. Because in our system, the tracking moves over the course of sort of a rotation once a day. So for engineers to calculate the lifetime of such a moving part, it's just so easy. They have wear calculations. They know how to do it, and it's just not a problem. Now, there's a motor that moves it. So you might say, well, what about the motor? Well, the motor actually has just one moving part. It's a brushless motor, and so it's just another bearing, and it has a similar characteristic. It's operating probably at 1% of its rated load, and it has a rated life, and that rated life is hundreds of years in this situation. So, so far what we found is that when we really show it to people, they go, yeah, I get it. The other thing is, let's say you have a building with 100 of these units on it, and they're all working just fine, and horror of horrors, 20 years later, one of them stops working. What happens? Nothing. The electric lights turn on, nobody even knows. It's just not an issue. So I'm going on here because it is something people very legitimately bring up. There's a bias against moving parts. But all I can say is when the experts look at the facts, the bias goes away. And they say, go for it. Yes?
My question is about the chain of R&D to field demos to outreach and
Yes.
tech transfer.
Yes.
Most of the time in the R&D world, in lighting, there's a marginal change, a slightly better widget, and it's fairly easy to gain traction in the marketplace in comparison to something that requires a fundamentally different change in the way a building is designed.
Right. So
my question is, have you thought about how to get through to the A&E firms?
Oh, very interesting. One thing I'll just throw out as a related factor is there's a very large market in deep retrofit, in major retrofit where you're replacing everything in the building. In fact, the two first projects that have been done were deep retrofit. We're now doing a couple of new buildings, and actually the one here will be, as you know, a kind of retrofit. So overall, we think that's an immediate opportunity. New construction, it is true that you at least want to get to the curtain wall makers and let them be aware of this opportunity. Interesting point. If you say, why don't we make this building solar ready? That's an easy decision to make because nothing has to change in the engineering of the building other than making sure the curtain wall is delivered with solar collection. Conversely, if you took a different approach and you said, look, maybe I'm not doing a curtain wall building, and I'd like to make it solar ready from a different point of view. I'd like to put in light fixtures that are efficient, high quality light fixtures made by a name brand fixture manufacturer, but I'd like them to be solar ready. So if I decide to put collectors on the building next year or the year later, I can do that. You can do it too. So there is an ability to mix and match there. When it comes to getting to the A&E firms generally, we think it's probably through the leading consultants. So, for example, a good friend of mine is one of the major national energy decision consultants. So his company, again, I probably shouldn't mention the name, but his company focuses on advising the A&E firms on the difficult, very complex trade-offs that get made in these building decisions, and he sees it as kind of a no-brainer. Not yet because it's not a catalog item yet, but once it's at the point that it's a catalog item and the data is there, he thinks it's a pretty easy decision to make. Excellent question. Thank you.
Is that filtered out? And with regard to sunlight, vitamin D is a big topic today. Does vitamin D get preserved?
No. Yeah, so the UV is taken out completely. And actually, and maybe this is a good question to wrap up on, Michael, if you like, because it's a very deep and important question on the health benefit of vitamin D, which is primarily from the UV component, and the other health benefits of a photochemical nature. So there are health benefits. I think some of you have probably heard of SAD treatments that involve light boxes and this sort of thing. So very important point there. At the light levels of indoor lighting, which we use for indoor illumination, you really don't get much activity in that space with electric lights or with daylight. I don't think daylight's better. I think it's about the same as electric light. It's not going to be worse, but it probably won't be better. We really think that if that's something of concern and you want health there, go for a walk at lunchtime. I think that's really the answer. And speaking of walking, thank you very much again.
Well, I want to say thank you very much, Professor and Margaret and family for coming out, and to everybody that came out this evening to see our first inaugural lecture. I would ask you to join us for drinks and food out in the lobby. So thank you so much for coming this evening.